Welcome back, everyone. We're diving back into the world of large language models today. Remember all those times we've talked about, all the incredible things these LLMs can do?
It's hard to keep up with all the advancements.
Yeah, exactly. Well, behind a lot of those advancements is something called the transformer architecture.
Right. Transformers have really revolutionized the field.
Yeah, and we've even talked about the groundbreaking attention is all you meet paper on the show before. It's brilliant. But there is a bit of a catch with all that self-attention magic.
It's a computationally expensive process, especially when you start dealing with really long sequences of text.
That's right. So it's like trying to have like a massive dinner party where everyone's trying to talk to everyone else at the same time. It can get pretty overwhelming.
That's a great analogy. The model needs to keep track of all the connections between words, and as the text gets longer, those connections multiply exponentially.
Exactly. So that's what has me so excited about this whole world of alternative LLM architectures. Researchers are coming up with all sorts of clever ways to, kind of match or even exceed the transformer's abilities.
They're finding ways to use less computational power, which is crucial, and handle even longer pieces of text, which opens up a whole new world of possibilities.
It's like finding ways to streamline that dinner party so everyone can still have meaningful conversations without the chaos.
Exactly. And there are a lot of different approaches being explored. Some are focused on making the attention mechanism itself more efficient, while others are ditching the attention idea altogether.
I'm all ears. Tell me more about these approaches.
Well, one way to make attention more efficient is to use something called linear attention.
Linear attention. How does that work?
It basically tries to simplify the way the model calculates relationships between words. Instead of considering all possible connections, it focuses on finding shortcuts that approximate the most important relationships.
So instead of everyone at the dinner party trying to talk to everyone else, they're focusing on having more targeted conversations with the people sitting closest to them.
Precisely. It helps reduce the computational burden without sacrificing too much accuracy. It's a delicate balancing act.
That makes sense. But wouldn't oversimplifying things make the model less accurate in understanding the text?
There's always a potential trade-off, yes. You might gain efficiency, but lose some of the nuanced understanding that full self-attention provides.
Got it. So it's like, it's like choosing between reading a detailed summary of a book or reading the whole thing. The summary's faster, but you might miss out on some of the subtleties.
That's a great way to put it, and that's why researchers are exploring other methods too, like sliding window attention.
So it's like limiting the model's field of vision to just a small window of text at a time.
Exactly. Instead of letting each word consider the entire text, you limit its focus to a smaller window of surrounding words.
So instead of looking at the whole dinner party, each person can only talk to the people sitting at their table.
Right. It makes the computation much faster, especially for really long texts. But of course, there's a potential downside. You might miss those crucial connections between words that are farther apart.
So you might miss the bigger picture. It's like trying to understand a movie by only watching a few scenes at a time. You could miss how the plot develops or how the characters relate to each other.
Exactly. And that's where things like global attention come in. It tries to combine the efficiency of local attention with a few global tokens that can capture those long-range dependencies.
Global tokens, it's like having a few designated people at the dinner party who are tasked with eavesdropping on all the conversations and reporting back any juicy gossip.
I love that analogy. It's like having a few scouts who can gather information from across the entire text and share it with the rest of the model. It's a way to maintain efficiency while still capturing the big picture.
It sounds like researchers are getting really creative with these approaches. Now, you mentioned that some approaches ditch the idea of attention altogether. That sounds pretty radical. Tell me more about that.
Yeah, this is where things get really interesting. One approach that's gaining a lot of traction is the use of state space models, or SSMs.
SSMs. That sounds more like something from a physics textbook than a conversation of our language.
You're not wrong. They have their roots in fields like control theory, where they're used to model systems that change over time. Like imagine a thermostat, the current temperature influences what the next temperature will be, and so on.
Okay, I can kind of see how that sequential thinking could apply to language. One word influences the next, building up meaning as it go along.
Exactly. And what's really cool about SSMs is that they're incredibly efficient at processing those sequences. It makes them ideal for handling those really long pieces of text that traditional transformers would struggle with.
It's like they're marathon runners built for endurance, effortlessly gliding through those long stretches of text.
I like that. And there's this one SSM-based architecture called Mamba that's been getting a lot of attention.
Mamba. Now, that's a name that sticks with you. What makes it so special?
Well, for one, Mamba uses something called selective state spaces. Imagine you're taking notes during a lecture, but you only jot down the most essential points. That's what Mamba does. It learns to remember only the most crucial parts of the text, which makes it incredibly efficient and effective.
It's like having a superpower for information filtering. only paying attention to what really matters.
Exactly. And Mamba was also designed with modern hardware in mind. Its algorithms are specifically optimized to run on GPUs, which are essentially the workhorses for these large models.
So it's like giving a powerful race car a perfectly tuned engine. It's designed for speed and efficiency.
You got it, and the results are impressive. In some tasks, Mamba has been shown to match or even outperform traditional transformers while being much more efficient.
That's amazing. But what about RWKV? I've heard that one's making waves too. It stands for Get This Receptance Weighted Key Value. Quite a mouthful, isn't it?
It is a bit of a tongue twister, but it represents another fascinating approach that ditches the attention mechanism altogether.
Really? So how does it process language without attention?
Well, it uses a combination of receptance and channel mixing to make sense of sequences.
Okay, I need a translation on that. What exactly is receptance?
Think of it as a measure of how receptive the model is to certain information. It learns to focus on the most relevant parts of the sequence while ignoring the rest, like a student who knows how to highlight the key points in a textbook.
So it's learning to prioritize information, kind of like a good student. And what about channel mixing?
Imagine different streams of information flowing through the model. Channel mixing is like having these control knobs that can amplify or dampen those signals, making sure the most important information gets through.
So it's like a DJ mixing different tracks to create the perfect sound.
Exactly. It's about refining and shaping the information as it flows through the model. And what's really exciting about RWKV is that it has something called linear computational complexity.
Linear computational complexity. Does that mean what I think it means? That it can handle longer and longer pieces of text without getting bogged down.
You got it. It's like a train that can keep adding cars without slowing down. And another key advantage is that it uses a constant amount of memory during inference. Unlike transformers, which need to store more and more information as the text gets longer, RWKV keeps its memory usage in check.
So it's like a suitcase that magically stays the same weight even as you keep packing more clothes into it. That's incredibly useful.
Absolutely, and that's what makes RWKV so intriguing. It has the potential to combine the strengths of both RNNs, known for their efficient memory use, and transformers, which are known for their ability to process those long sequences.
It's like getting the best of both worlds, and it seems like efficiency is a common thread in a lot of these new approaches.
Definitely. Computational efficiency is a major focus in LLM research right now. We're trying to find ways to achieve the same level of performance as transformers while using fewer resources.
Now, before we move on to even more groundbreaking architectures, I'm curious about one that's been on my radar. Hyena. What's the story with that one?
Ah, yes. Hyena is another interesting contender in this race for efficiency. It uses a combination of long convolutions and a gating mechanism.
Okay, now break that down for me. What exactly are long convolutions, and how do they help with language processing?
Imagine you're reading a book, but instead of going word by word, you can take in larger chunks of text at once, like whole sentences or paragraphs. That's essentially what long convolutions allow Hyena to do. It can process information in larger units, which makes it much more efficient.
So it's like speed reading, but for AR. You're still getting the meaning, but at a much faster pace.
Exactly. And the gating mechanism acts like a filter, helping the model decide which information is important and which can be safely ignored.
So it's all about processing information intelligently and selectively. It sounds like Hyena has a lot of potential for tackling those really complex and lengthy texts without getting overwhelmed.
That's the idea. And then there's another approach that we shouldn't forget about, mixture of experts, or MOE.
Oh yeah, MOE, we've talked about that before. It's like having a team of specialists, each with their own area of expertise.
Exactly. But when we're talking about LLMs, we're particularly interested in what's called sparse MOE. That's where only a subset of those experts are activated for any given input.
So it's like assembling a dream team of experts, but only calling upon the specific skills needed for each task.
Exactly. It's a way of making those huge models more efficient by only activating the parts that are truly relevant at any given time. A good example of this is the switch transformer, which has shown remarkable scaling capabilities.
It's like having a toolbox full of specialized tools and only picking out the ones you need for a particular job. No need to carry around the whole toolbox all the time.
That's a great way to think about it, and that's what makes this whole landscape so fascinating. We're seeing so many different approaches, each offering unique solutions to the challenges of LLM efficiency and performance.
It's like a grand experiment in AI architecture, with researchers trying out all sorts of ideas to see what works best.
Exactly, and the best part is we're really just at the beginning of this journey. There's still so much more to explore and discover as we continue to push the boundaries of what these models can do.
It's an incredibly exciting time to be following this field. So many possibilities.
Absolutely. And speaking of possibilities, one of the most crucial aspects of LLM development is the data they're trained on. We can have the most amazing architectures in the world, but without the right data, well, it's like having a state-of-the-art kitchen but no ingredients.
That's a perfect analogy. And that's actually a great segue into the next part of our deep dive.
Let's talk data.
I'm ready to dig in.
We often talk about LLMs like they're magic, but in reality, the magic really comes down to the data they're trained on.
Yeah, it's kind of like that saying, you are what you eat, right?
Exactly. If you feed an LLM a bunch of junk data, it's not going to produce anything worthwhile.
It's like trying to bake a cake with spoiled milk and rotten eggs. No matter how good your recipe is, the cake's going to be a disaster.
Haha, that's a great way to put it. So when we talk about LLM data, it's not just about quantity, it's about quality.
Right, so it's not just about throwing as much data as possible at the model. It's about being selective and thoughtful about what kind of data we use.
Absolutely. And there are three key qualities that we look for in a good LLM dataset: diversity, quality, and alignment.
Okay, let's break those down, starting with diversity. What does that mean in the context of LLMs?
Well, imagine you're teaching someone a new language. You wouldn't just teach them a few basic phrases. You'd want to expose them to a wide range of vocabulary, grammar, and styles of speaking.
So it's like giving them a well-rounded education in the language.
Exactly. And it's the same with LLMs. We want to train them on a diverse data set that covers a wide range of topics, writing styles, and genres.
So that means including everything from news articles and scientific papers to novels, poetry, and even code.
Precisely. This breadth of exposure helps the model develop a more nuanced and flexible understanding of language.
It's like giving the model a passport to explore the entire world of language.
That's a great way to put it. And diversity isn't just about the types of text, it's also about the sources of that text.
Right, we want to make sure that the data represents a variety of voices and perspectives.
Exactly. Including data from different cultures, languages, and backgrounds is crucial for mitigating bias and creating a model that reflects the real world.
It's like making sure that everyone has a seat at the table when it comes to shaping the LLM's understanding of the world.
I love that analogy. Now let's talk about quality.
Yeah, what does it mean to have high-quality data for LLMs?
Well, think about it like building a house. You wouldn't use shoddy materials, right? You'd want to use strong, durable materials that are free from defects.
So it's about making sure that the data itself is accurate, consistent, and reliable.
Exactly. We want data that's well-written, well-structured, and free from errors, contradictions, and ambiguities.
So it's like making sure that the foundation of the LLM is solid and trustworthy.
Precisely. And that often involves a lot of cleaning and pre-processing to remove noise-correct errors and standardize the data.
It's like taking those raw ingredients and carefully preparing them before you start cooking.
That's a great way to think about it. And then there's the third quality, alignment.
Alignment. What does that mean in the context of LLM data?
It's about making sure that the values and goals that we want the LLM to embody are reflected in the data.
So it's not just about feeding the model any kind of data. It's about being mindful of the messages that data might be conveying.
Exactly. If we want to create LLMs that are helpful, harmless, and unbiased, we need to be intentional about the data we use to train them.
It's like raising a child. We wouldn't just let them watch any TV show or read any book. We'd want to make sure that they're exposed to content that's appropriate and aligns with our values.
That's a perfect analogy. Alignment is all about shaping the LLM's behavior and making sure that it's used for good.
So it's like setting the moral compass for the model.
Exactly. Now that we've talked about the qualities of good LLM data, I'm curious to hear about the specific types of data that are commonly used.
Yeah, what are some of the go-to sources for LLM training?
Well, some of the most common sources include text scraped from the web books, code repositories, and scientific papers.
Okay, let's dive into each of those, starting with text scraped from the web. I imagine that's a pretty vast and messy source of data.
You're not wrong. The web is a treasure trove of information, but it's also full of noise, inconsistencies, and biases. Extracting useful data from the web requires sophisticated techniques for crawling, filtering, and cleaning the text.
It's like trying to pan for gold in a river. You have to sift through a lot of dirt and debris to find those precious nuggets.
That's a great analogy. And even with the best tools, there's always a risk of incorporating biases from the web itself.
Right, because the web is a reflection of our society with all its complexities and imperfections.
Exactly. So it's important to be aware of those biases and to take steps to mitigate them.
Now, what about books? They seem like a more curated and reliable source of information.
They can be. Books offer a wealth of well-written structured text that can be very valuable for training LLMs. They provide deep dives into various topics, styles, and genres.
It's like giving the model access to a vast library of knowledge.
Precisely. But even with books, there are things to consider. The selection of books can introduce bias. So if you primarily use books from a particular culture or time period, that bias will be reflected in the LLM.
So it's like curating a reading list for the model. You want to make sure that it's balanced and representative.
Exactly. Now, what about code repositories? They seem like a unique and potentially very valuable source of data.
Yeah, I'm curious to hear more about that. What kind of insights can we gain from code?
Code repositories like GitHubs are treasure troves of structured logical text. They can teach LLMs how to think like programmers.
So it's like giving the model a crash course in coding boot camp.
Exactly. And using code data is a growing trend in LLM training. We're seeing models that can generate code in multiple programming languages, translate code from one language to another, and even write documentation.
It's like the LLM is becoming a multilingual coding wizard.
That's a great way to put it. And training on code can actually improve the LLM's ability to reason logically and follow structured instructions.
So it's like teaching the model to think more systematically and precisely.
Exactly. And finally, we have scientific papers, which are a gold mine of specialized knowledge.
Yeah, I imagine they could be incredibly valuable for training LLMs that need to understand specific domains.
You're absolutely right. Scientific papers are packed with factual information, technical language, and rigorous reasoning. They can teach LLMs about complex topics in fields like medicine, physics, engineering, and more.
It's like giving the model a PhD in every scientific field.
Exactly. And this type of data is being used to develop LLMs that can assist scientists with research, help doctors diagnose diseases, and even accelerate the pace of scientific discovery.
It's like giving researchers a superpower in the realm of knowledge discovery.
Precisely. So we've talked about these different sources of data, but I'm curious about the actual process of creating an LLM dataset. How do you go from a mountain of raw text to a well-structured, usable dataset?
Yeah, it sounds like a pretty daunting task. What are the key steps involved?
It's definitely a multi-step process. It starts with data collection, then moves on to cleaning and pre-processing, followed by formatting and structuring, and finally evaluation and quality control.
Okay, let's walk through those steps one by one, starting with data collection. What does that entail?
Data collection involves gathering all the raw text from the various sources we've discussed. It's like sending out a team of explorers to map the vast landscape of human knowledge.
That's a great analogy. So once you've gathered all this raw data, how do you make it usable for training an LLM?
That's where cleaning and pre-processing come in. Think of it like taking those raw data gems and polishing them until they sparkle. You need to remove all the noise, inconsistencies, and errors so that the model can learn from clean, consistent information.
So what kind of tasks are involved in this cleaning and pre-processing stage?
It really depends on the data source. If you're working with web data, you might need to remove HTML tags, correct spelling errors, standardize punctuation, or convert all the text to lowercase. If you're working with books, you might need to remove headers, footers, or page numbers.
It sounds like a very meticulous process.
It is. Its attention to detail is crucial at this stage.
And what happens after the data is cleaned and pre-processed?
Well, the next step is formatting and structuring the data in a way that the LLM can understand. This typically involves tokenization, which is the process of breaking down the text into smaller units that the model can process.
So it's like chopping up the ingredients before you put them in the pot.
Exactly. And then finally, we have evaluation and quality control. This is where you make sure that the data set is accurate, consistent, and aligned with your goals.
It's like giving the data a final inspection before you serve it up to the LLM.
Precisely. You want to make sure that the model is being trained on the highest quality ingredients possible.
Now, creating an LLM dataset from scratch sounds like a very time-consuming and resource-intensive process. Are there any shortcuts?
There are many existing LLM datasets that people can use. Both open source and commercially available datasets cover a wide range of topics, languages, and sizes.
So it's like having a menu of pre-made dishes to choose from.
Exactly. And these datasets can be a huge time saver for researchers and developers who don't have the resources to create their own datasets from scratch.
That's great. Now, I'm wondering how much data is enough to train a good LLM? Is it just a case of the more the merrier?
That's a question that researchers are still grappling with. There's definitely a general agreement that LLMs benefit from huge amounts of data, but there's no magic number that guarantees a good model.
So it's not just about blindly throwing more data at the problem.
Right. The optimal data size depends on a lot of factors like the complexity of the task, the desired level of performance, and the computational resources you have available.
It's like figuring out how much fuel a rocket needs to reach the moon. It depends on the size of the rocket and how far it needs to travel.
That's a great analogy. And just like with rockets, there's a point of diminishing returns. Adding more data beyond a certain point might not significantly improve the model's performance, and it can even lead to overfitting.
Overfitting, what's that?
Overfitting is when the model becomes too specialized to the training data and doesn't generalize well to new, unseen data. It's like a student who memorizes the answers for a test but doesn't actually understand the concepts. They might ace that specific test, but they'll struggle when faced with new material.
So it's like the model's becoming too rigid and inflexible.
Exactly, and that's why finding the right amount of data is a balancing act.
You want to give the model enough data to learn effectively, but not so much that it becomes over-specialized.
Precisely. It's a delicate dance between data quality and quality computational resources and performance goals.
This whole discussion about LLM data has been incredibly insightful. It's amazing to see how much effort goes into creating these data sets and how crucial they are for the success of LLMs.
It really is a fascinating area, and as the field of LLMs continues to evolve, we're likely to see even more innovative and creative approaches to data curation.
Now that we've covered the architecture and the data, I'm really curious to hear about how all of this translates into real-world applications.
That's a great question, and that's exactly what we'll be diving into next.
So we've talked about all these different architectures and this massive amount of data that goes into training LLMs, but how does it all actually come together? Like, what are some real-world examples of how this technology is being used?
Yeah, that's the exciting part, right? Seeing how all this research and development translates into real-world impact.
Exactly. Like, how are LLMs actually being used to solve problems that make a difference?
Well, one area where we're seeing a huge impact is in customer service. Think about those chatbots you encounter on websites or in messaging apps.
The ones that sometimes leave you wondering if you're talking to a real person or not.
Exactly. Well, more and more of those chatbots are being powered by LLMs trained on massive data sets of customer interactions.
So they're learning how to talk to us like real customer service agents.
Yeah, they're learning to understand customer queries, provide helpful responses, and even resolve issues without any human intervention.
Wow, that's pretty impressive. It's like having an army of virtual assistants ready to help us out 24/7.
Right. It can be a real game changer for businesses, too. It can improve customer satisfaction, reduce costs, and even open up new avenues for a personalized service.
It's like giving businesses a superpower when it comes to customer experience. And I imagine this approach is transforming other areas too, like how we create and consume content.
Absolutely. Think about the articles you read, the marketing copy you encounter, or even those social media posts that pop up in your feed. A lot of that text is being generated or at least assisted by LLMs trained on vast amounts of written content.
So in a way, these LLMs are learning to write like humans.
In a sense, yeah, they're picking up on the patterns and nuances of human language and using that knowledge to generate everything from news summaries to product descriptions to even poems and scripts.
That's pretty wild. So are we heading towards a future where robots will be writing all our content?
Well, it's not quite that extreme, but I do think we're moving towards a more collaborative model where humans and AI work together in the creative process.
It's like having a writing partner who's always available and never gets writer's block. Pretty handy.
Right, and it can really boost creativity and open up new possibilities. Now, another area where LLMs are making a big impact is in research, especially in fields where there's just a ton of information to sift through.
Yeah, like in scientific research where there are mountains of papers and data to analyze.
Exactly. LLMs are becoming really powerful tools for navigating that sea of information.
It's like having a research assistant who can read and analyze thousands of papers in the blink of an eye. It frees up researchers to focus on the big picture stuff.
Exactly, and it has huge implications for speeding up scientific discovery, deepening our understanding of complex phenomena, and even developing new treatments for diseases.
It's like giving researchers a superpower in the realm of knowledge discovery.
I like that. And really, we're just scratching the surface of what's possible with LLMs. As the technology continues to evolve and data becomes even more abundant, we can expect to see even more amazing applications emerge.
It's truly an exciting time to be witnessing this technological revolution. But amidst all this excitement, I think it's also important to acknowledge that there are some challenges and ethical considerations that come along with this powerful technology.
Oh, absolutely. We can't just blindly embrace this technology without thinking about the potential downsides.
Right. We've touched on some of the ethical implications before, but maybe we can delve a bit deeper into those now. Like, what are some of the practical challenges that need to be addressed when it comes to LLMs?
Well, one of the biggest concerns is data bias. Remember, LLMs learn from the data they're fed, and if that data reflects societal biases, the model will inherit those biases too.
It's like teaching a child with outdated or prejudiced textbooks. They're going to learn the wrong lessons.
That's a good way to put it. And those biases can have serious real-world consequences, perpetuating harmful stereotypes and leading to unfair or discriminatory outcomes in important areas like hiring, lending, or even criminal justice.
It's a sobering reminder that technology isn't neutral. It carries the imprint of its creators and the data it's trained on. So how do we address this issue of data bias?
It's going to take a multi-pronged approach. We need to be much more careful about curating and evaluating the training data developed techniques to detect and mitigate bias, and be much more transparent and accountable in how these models are developed and deployed.
It's like we need to build safeguards into the system from the ground up.
Yeah. Another big challenge is the issue of explainability. LLMs are often called black boxes because it can be really hard to understand how they arrive at their outputs.
So we see the results, but we don't really know the reasoning behind them. It's like getting a medical diagnosis without understanding how the doctor came to that conclusion.
Exactly. And this lack of transparency can be a problem in areas where trust and accountability are crucial, like in healthcare, finance, or the legal system. There's a lot of research going on right now to try to make LLMs more explainable so we can understand how they work and have more confidence in their outputs.
It's like we're trying to open up that black box and shed some light on the decision-making process.
Right. And that ties into another challenge, which is control and safety. LLMs are incredibly powerful tools, but they can also be unpredictable. There's always a risk that they might generate outputs that are harmful, offensive, or just plain nonsensical.
We've all seen examples of those hallucinations where the model just spits out something completely bizarre. It might be funny in some contexts, but in others it could be really problematic.
Exactly. So it's super important to develop ways to control these models, prevent them from generating harmful outputs, and ensure their safety and reliability when they're used in the real world.
It's like we're trying to put guardrails around this incredibly powerful technology so it doesn't veer off course.
Right. And this involves developing robust safety mechanisms, testing and evaluating models thoroughly, and establishing clear guidelines and ethical frameworks for how these models are used. It's about setting the rules of the road for this new technological landscape.
And I imagine there are other considerations too, like data privacy and the potential impact of this technology on jobs and the economy.
Absolutely. It's a complex landscape with a lot of different factors to consider, but I think the key takeaway here is that the development and deployment of LLMs require not just technical expertise, but also a deep understanding of the ethical, societal, and economic implications of this technology.
It's not just about building cool technology, it's about building technology that's beneficial and responsible.
Exactly. It's a call for collaboration and thoughtful innovation, bringing together experts from different fields to make sure we harness the power of LLMs for good while mitigating the potential risks.
Well, this has been an incredibly fascinating deep dive. I feel like I've learned so much about the potential of LLMs, the challenges we need to address, and the incredible possibilities that lie ahead.
I'm glad to hear that. It's definitely a topic that sparks a lot of curiosity and discussion, and I hope our listeners are feeling just as inspired and intrigued as we are.
Me too. And as we wrap up this episode, I think the biggest takeaway for me is that we're still in the very early stages of this technological revolution. LLMs are rapidly evolving, and we're only just beginning to understand their true potential.
That's right. It's an exciting time to be involved in this field, and I'm really looking forward to seeing what the future holds for LLMs.
Me too. And to our listeners, we encourage you to keep exploring, stay curious, and join us again for our next deep dive as we continue to explore the ever-evolving world of technology and innovation.